tides. Why do tides happen? A little demonstration of what tides are. These are tides from the Bay of Fundy in Nova Scotia. Some of the largest tides in the world, 38 feet. So you can see what happens. The boats are beached. You can't take them out. And the water comes in and really raises it a lot. This is a floating dock. So any dock that's put in a place where there's a lot of tide on the ocean, they put it floating at the end because the tides rise and fall. We need the dock to be able to adjust to the ocean level. So this is sped up at something like 360 times or 3,600 times the speed. So the boats look like they're rocking about wildly, but really it's just rocking back and forth slowly. Yeah, so those are tides. So maybe you have some back knowledge of tides, you've seen them before, maybe you've been to the ocean, you go to the beach, there's a high tide line, a low tide line. So this is just kind of a more dramatic example. You know, if you go to the beach in Boston, the tides aren't this big, but they go up and down by, say, 5 feet or something. So why do the tides happen? I ask my students this, and right away they're like the moon, which is true. Everybody knows the moon is involved in tides, but we're not quite exactly sure how. So keep in mind, there are 2 high tides per day. Why would you get 2 per day if it's just the moon pulling on it? If this is the moon here, then I'd expect, okay, a bunch of the ocean gets kind of pulled towards the moon, but why would there be this bulge on the far side? I would just expect that the moon would pull a bunch of the ocean and you get 1 high tide a day, yet we get 2 high tides a day. So it's this big mystery. And the answer has to do with the differences in the forces. So tidal forces are this thing that happens whenever you've got a gravitational effect and the field of the gravity is taking place over a very large area. So for example, the Earth is a huge volume of space. So the result of this is that the amount of force felt is very different depending on where you are. So this becomes an important thing. So this happens in the case of the Earth, the Moon. It happens in the case of any astronomical body, which is so big that the gravitational field, the acceleration of the gravity, varies a lot over the object. So basically, it's not just about the amount of force. Right? If this is the Moon right here, and this is the Earth, then we'd say, okay, well, the Earth is pulled this way, but why would the ocean be pulled more than the Earth? Like they all experience the same acceleration as caused by the moon, right? Why would parts of the Earth get pulled more? Why would the water be pulled more than the land? So the answer is, this is kind of the average amount of force on the whole Earth from the moon, but the closer parts are pulled more strongly. The further parts are pulled more weakly. And then, if you're here, you kind of get pulled that way. If you're here, you kind of get pulled that way. So the idea is that I don't really notice this overall force on the Earth because everything on Earth feels it. It's a matter of the fact that different parts of the Earth feel a different amount compared to that overall average. So what I do is I take this average force and I subtract it off of what the force is everywhere. The overall result is, because this is a bigger force than the average, the difference is still in this direction. Since this is a smaller force than the average, it's still in this direction. And then there's also an important effect from the sides of the Earth that are kind of off to the side of the moon, peripheral to the moon, lateral to the moon, language. And there, if I subtract off the difference, so again, this force is coming towards the moon, but if I subtract off the average force the Earth feels, then I get a force going inwards towards the Earth. So that's the overall shape that I get. And the result of that is these parts of the Earth get pushed in, the water gets pushed in, and these parts of the Earth, the water gets pulled out. And the reason why this affects the water and not the land is the water can flow. If the water feels a force, it can move around and flow. And so what happens is it bulges out in certain places. This isn't really showing up, but basically, if this is a perfect sphere, I can kind of exaggerate what the tides look like. So So these parts get sort of squashed in, and that water, it's like a tube of toothpaste thing, that water gets pushed outwards to the ends there. So this is called a tidal force. So as the Earth rotates, you get into high ocean parts, you get high tide. You get into low ocean parts, you get low tide. And that's where the tides come from. So again, it's really confusing to explain because it's not about the overall force, it's about the difference from the average. That's what you notice. So the example I was doing in class, I had one student sort of standing in the middle, and the idea is that I had one student pull, I had students pulling from both sides. And the idea is that, again, I'm going to try to explain this again. This part of the Earth here is getting pulled more than the rest of the Earth, so the net force, the difference force, is that way. So what's happening is, okay, this part of the Earth, this part of the water gets pulled more than the average Earth. The part that's a little harder to understand is this water is here, because this is the part of the Earth that's getting pulled less. So this is like the Earth that's getting left behind as the rest of Earth gets pulled this way. So this gets left behind, this is feeling the average, and this gets pulled a little bit more than it. So it stretches the thing out. And this is related to why we only see one side of the moon. So you haven't seen this side of the moon. This is like the acne side of the moon. You've only seen it because I've shown you pictures. You've looked online for pictures. You've never seen this in person. You've seen this side of the moon, because that's what it looks like. We always see the same face. And the reason for this is it's called tidal locking. So the idea is that just as the moon creates a tidal force of the Earth, stretching it out and kind of squashing it, the Earth, in the other direction, creates a tidal force in the moon. So the moon doesn't stay perfectly spherical. It gets stretched out a little bit. So the result of that is that this closest little piece of the moon kind of gets locked into this closest little piece of the Earth, and they stay in together. So that's why you get this tidal locking, and you get the same face of the moon always pointed towards the Earth. And this happens in a lot of other examples in the solar system. You look at Jupiter or Saturn's moons; those are tidally locked with their host bodies, with Saturn and Jupiter respectively. And it does happen. And in fact, the tidal locking happens so much that there's this extra effect that goes on, which is eventually the speed that the host body rotates at matches up with the speed the moon goes around it. So with Earth, the moon goes around once every month, 27, 28 days, but the Earth spins around once every 24 hours. What's actually gradually happening is the Earth is actually slowing down, and the moon is actually months are getting faster. At some distant time in the future, I don't know, millions, billions of years or something, they'll be synchronized. So an Earth day will be a little bit longer, and the moon month will be short enough to match it. And this actually has a name, the tidal force. Whenever it gets extreme, it's actually called spaghettification. Fortunately, I can't really zoom in on that. Spaghettification. And it's basically this tidal effect that you get whenever you're near a strong amount of gravity. So this especially happens near black holes. And the idea is if you get near a black hole, if your feet are closer to the black hole than your head, all of you gets pulled, but your feet get pulled really strongly, much more than your head. So what happens is you get stretched out. My students say, that's great, I'll be taller. Well, you're going to get a lot taller than you ever want to be. So that's the effect of tidal forces. So I encourage you guys to read up about that if you want to know more.